What?
Isn't that
I probably messed up.
Isn't it
2 root 2 is negative actually, so yeah, that's pretty bad. Okay. 2 root 2 is like negative 2.8. So actually, this function is down here. So I guess it looks like that. Yeah, I mean, okay, now you're forcing me to think. So this is root x, like root x minus 2, right? So this is going to kind of have like a, this function is going to have, so it doesn't look like that either. This function is going to cross at root 2. It's going to have a root, right? So it's going to be positive x minus 2.
No,
Oh yeah, 4. Oh man, I'm making so many mistakes on video too. So yeah, so it's going to be negative until 4 and then positive thereafter, right?
Yeah.
So the function looks kind of like that. Now I'm reasonably confident that I'm doing the right thing. And however, we're only interested in the function on this interval. So, good. So I'll just like put dashed lines or something over here because I don't care about that. So on this interval, what can I say about the function on the interval from 0 to 2? Well, there exists some point, according to the mean value theorem for integrals, there exists some point at which the function obtains its average value. And the average value of the function is the place where like that area equals that area. Okay, so this is really a two-step problem. Figure out what the average value of the function is, and then find the point where the function obtains its average value. What is the average value of a function? By definition, the average value of f on the interval 0, 2 is 1 over 2 minus 0 times the integral from 0 to 2 of x minus 2 root x dx. So let's compute this integral. Well, it's 1/2 integral from 0 to 2 of x minus 2x to the 1/2. So that is going to be, now I anti-differentiate, and it's x squared over 2 minus, whoa, I'm having trouble anti-differentiating today. Oh yeah, 3/2, so 2/3, 4/3 x to the 3/2. And that's 2 and that's 0. Okay, so now I continue with my algebra here, or really I'm just doing arithmetic now. That's 4, so that's 2 minus, and then this gets kind of gross, right?
Yeah.
Because that's like 2 root 2. Right? Yeah, root 8, that's 2 root 2. So it's 8 root 2 over 3. God, is this really the right answer?
Yeah.
I guess it is. So that final answer is 1 minus 4 root 2 over 3. All right, that is the average value. So that is kind of the important part of the problem in my opinion, but then your textbook likes to give you a little and it wants you to actually find the point C where the function equals that. And then now this just becomes like a pretty hard algebra problem basically, right? So when does x minus 2 root x equal 1 minus 4 root 2 over 3? I mean, do you want to do this?
No.
There's some cool way to do it, but I kind of can't remember. I think you like complete the square or something, right?
Yeah, add 1.
Yeah. If I add 1 to both sides, then you get x minus 2 root x plus 1 equals 2 minus 4 root 2 over 3. Why would I do that? Because now this becomes root x plus 1 squared equals
Minus 1 squared.
minus 1 squared. And then this is then just like 6 minus 4 root 2 over 3. And now I take the square root of both sides. Believe it or not. So I get root x minus 1 is root of that. Plus minus probably, but one of them is going to get ignored because it's like not on the interval. But so we finally get that root x is 1 plus or minus root 6 minus 4 root 2 over 3. And then you square it. So x is 1 plus or minus root 6 minus 4 root 2 over 3 squared. CalChat probably just assumes that you just use your calculator at this point, right? Did anyone check this out on CalChat? No. Did they just reach for the calculator now?
The book has decimal answers.
The book has decimal answers. So the final answer, I guess, is going to be which one is it's going to be one of those two.
It's both, man.
It's both?
Because 6 minus 4 2 is like less than.
Oh, so both of them work. So there are actually two places where it happens, which means my graph is probably pretty bad. It means that I must have curved. The minimum's at 1, so it means it curves up a little bit more like that, right?
Yeah.
Yeah. Okay. All right. Good, guys. We suffered together. It was a bonding experience. Good problem. More. Let's do like 2 more problems and then move on. 85, 89, 109. Which of those are important?
Actually, no, I kind of do. 85 is not.
85. Oh, I think 85 is okay, right? Yeah. 85 is just kind of what we've been doing. I'm going to skip that. 89. Oh yeah, this is like kind of silly. This is a little bit of a silly problem, 89. But anyway, we'll just do it. 89 gave you some accumulator function. And I think what possibly made this problem confusing is that what the book calls the second fundamental theorem of calculus is what we did first. And what the book calls the first is what we did second. But anyway, basically the directions are, first, integrate. In other words, first just do this. Okay, so let's do it. If we do it, according to the FTC, the antiderivative of x to the 1/3 is 3/4 x to the, or 3/4 t to the 4/3. Evaluated at x and 8, right? This is what they had in mind. And now, if we just evaluate, this becomes 3/4 x to the 4/3 minus, and 8 to the 4/3 is like 16, so this is minus 12, I think. Yeah. So that was part A. And then part B, what they wanted you to do was to demonstrate the fundamental theorem of calculus by instead, wait, is that what they wanted you to do? Integrate. Oh, and then what they wanted you to do was, so if that's f, so our conclusion from part A is that f is in fact just, big F in fact is just the function 3/4 x to the 4/3 minus 12. And then part B they say, hey, take the derivative of that. What is the derivative of f prime? It is, well, differentiating this, I get x to the 1/3, that's it. Okay? And so, right, I'm just kind of like, I'm just sort of verifying that, in fact, that fundamental, alright, that's all. That's all that problem was. Alright, 109 is actually a deep problem of importance. I think I did a good job teaching this subject this year, so maybe I'm hoping for good results. 109 was a thinking question, but it was phrased actually a little bit awkwardly. So let's ignore their phrasing and let's just do the problem. If you ignore what was in their black text and you just kind of like read what you were supposed to do, here was what you were supposed to, or here is what they wanted. So first of all, they give you some position function, and the position function is t cubed minus 6t squared plus 9t minus 2. And yeah. And here are the directions. Oh, and they tell you this is specifically t is to be on the interval from 0 to 5. Directions. Find the total distance the particle travels in 5 seconds. So find the distance traveled on the interval 0, 5. Okay. Well, anytime you hear the word distance, your brain should immediately throw up a red flag, because, Sid, we don't use these terms loosely in calculus context. If they say distance, they mean distance. So there's an easy question, which I can answer right away, which is the displacement. What would the displacement be? This is not what they're asking. but just to get that out of the way, we could ask that question. Well, they're giving me the position function. And so the displacement is not a difficult question to answer. The displacement on the interval 0, 5 is just x of 5 minus x of 0. And what is x of 5? Okay, let's give me some big numbers. Someone do it. 125 minus, I'll do it, I guess. 125 minus 150 is negative 25, and 45, negative 20, negative 22. Someone back me up there.
I did not.
What?
No.
I did
I
not.
think it's wrong.
No.
Let me try again.
18.
Yep, you're right. Okay, good. So the answer is 18. Okay, but all that means
Wait.
is that.
No, it's
Oh.
20. It's
Let me try
20.
again.
18 minus 2.
18 minus, no, it's 18 minus,
minus 150.
It's
negative 2,
It's
it's 20.
negative 25 and 45. 20 minus 2 is 18.
But it is 18.
Minus x of 0, which is negative 2. So the answer is 20. Okay. So, all that tells me, thank you, Christine. All that tells me is that I started at time 0 at negative 2, and at location negative 2, and I ended at time 5 at 18. So if you want to make a picture, here's 0. I'm moving about this number line haphazardly according to some kind of function, which is this one. At time, here I am at negative 2 at time t equals 0, and later on I'm here at position 18 at time t equals 5. And so the answer to the question is I have moved 20 to the right on this interval. Okay, but that's not what they're asking. They want to know the actual distance traveled. And since this is cubic, I expect that this function's like going back and forth, right? So the actual particle starts here, and he probably does a bunch of stuff, and he ends here. So how can we find the distance traveled? Well, one way to do this, one way to do this is to just, well, let's figure out where he was moving to the left and where he's moving to the right. So let's differentiate x. And if we differentiate x, we get 3t squared. I actually don't need the fundamental theorem of calculus really to do this problem, actually. So this 3t squared minus 12t plus 9, I think that factors nicely. So t squared minus 4t plus 3. And so this is 3t minus 3, t minus 1. This is actually a really important problem. It's like, puts kind of everything we've been doing together. That is the derivative of the position. Since that's the derivative of the position, let's make a sign chart. And the sign chart is going to look like this. Start at 0, we'll end it at 5, and there's a sign change at 1 and at 3. This is quadratic, it looks like this. So it goes positive, negative, positive. Which means that I'm moving to the right on the interval 0, 1, I'm moving to the left on the interval 1, 3, and I'm moving to the right on the interval 3, 5. Okay? So one way to do this that actually has nothing to do with intervals, because they give you the position function, let's just answer the question, all right, how much distance was covered on the interval 0, 1? Well, since I'm moving to the right that entire interval, I can simply take x of 1 minus x of 0.
Can you just do I guess, yeah.
I'm going to get to that in a second, right? X of 1 minus x of 0. Does everyone agree that that represents the displacement on the interval 0, 1? But since I was moving to the right that entire time, the displacement is also equal to the distance traveled on the interval 0, 1. Okay, plus, so plus, all right, I guess I'll write plus. But now something happened, right? Now I'm moving left on this interval. So, I guess, okay, how should I say this? So I need to figure out how much distance was covered on this interval. But since I'm moving left, which of these numbers is going to be smaller? The position at 1 or the position at 3?
3.
The position at 3 is going to be smaller because I'm moving the other way. So I can kind of write this as x of 3 minus x of 1, but I have to know that what kind of number is that going to be? Negative. This is going to be a negative number right here. This is going to be a negative number because I know that the displacement is negative on the interval 1, 3 because I'm moving to the left. and since it's a negative number and I want to add distances, I'm going to put a negative in front of it. Is this logic making sense? This is like almost like, this is like the whole course in like one problem kind of, in some ways. And then now starting at 3, I'm moving to the right. But if I'm moving to the right now, I need to add the distance traveled on the interval 3, 5, so that's x of 5 minus x of 3. And that is going to be a positive number. So I kind of like know by logic that that's going to be a positive number, that that's going to be a negative number, and that that is going to be a positive number. But by splitting up the interval into places where it's either all moving left or all moving to the right, then does everyone agree that this will give me the total distance traveled? Okay, so and I don't actually feel like doing it, but if you do all those, plug in all those numbers, then you're going to get the right answer. All right, alternatively, the book tells you to do this strange thing. It says, take the derivative, which we actually did, and then it says that the distance traveled, so the distance traveled is going to be the integral from 0 to 5 of the absolute value of the derivative of the position function. What the hell is that about? Well, maybe we make a graph of this. Yeah, that's what we should do. Make a graph of this velocity. So if we make a graph of velocity, when I plug 0 into velocity, I'm going to get 9. When I plug 1 into velocity, I get 0. When I plug 3 into velocity, I also get 0. And then when we plug 5 in, didn't we do this already? Or no, we didn't. If I plug 5 in, I get 2 times 4 times 3, 24. Okay, so picture not to scale. My velocity function basically looks like this, right? Okay. And so now graphically, if I take the integral from 0 to 5 of velocity, what is that going to give me? This is going to give me this is going to be x of 5 minus x of 0, which is going to just give me, the displacement. That's not what I want. We already calculated. That is 20. That is correct, but this is not what I'm interested in. What I'm interested in is the distance traveled. So how could I do this? Well, take the absolute value. If you take the absolute value of a velocity function, then you turn it into a speed function. So the absolute value is going to look like this. And if you take the integral from a to b of some velocity function is going to give you the displacement. Displacement on the integral ab. But if you take the integral from a to b of the speed of a speed function, that is going to give you the distance traveled. Does this make sense? On the integral ab. So what the book is telling you to do is to, in order to calculate the distance traveled, take the derivative of x, which gives you the velocity. Take the absolute value of the velocity, which gives you the speed, and then take the integral of that, which is equivalent to taking the integral to finding this area, and that will be the total distance traveled. The distance that I covered on the interval 0, 1 when I was moving to the right, the distance that I covered on the interval 1, 3 when I was moving to the left, and blah, 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 blah. And by the way, if you wanted me to actually do this integral, it's like that problem we did over there when you guys asked, hey, how would you do this if it wasn't so simple where I could just draw a picture? And the answer was, you split it up. So if someone just gave me, the integral, if someone actually just said, hey, dude, do the integral from 0 to 5 of the absolute value of 3t minus 1, t minus 3, how would I, in practice, compute this integral? I would just have to figure out where it was positive and negative, and I would have to split it up. I would look at that picture and I'd say, oh, okay, well this is the integral from 0 to 5 of the velocity. No, sorry, it's the integral from 0 to 1 of the velocity, because I know that's going to be a positive number. Minus the integral from 1 to 3 of the velocity, because I know that's going to be a negative number, plus the integral from 3 to 5 of the velocity, because I know that's going to be a positive number. And this exactly matches what we got over here without using integration. All right, that was a decent explanation. Angel, you got this? Okay, Aaron Sankar, this all making sense? All right, can I have this homework?
Me too.
Yeah. All right, two things. One of which we sort of did already last class. So, but maybe this time I'll try to do it a little bit more carefully. There is this kind of application of the fundamental theorem of calculus. Really, this is kind of just a cheap way of textbooks to sort of to test to see if you really understand what you're doing. We talked about this. Let's just kind of talk about it again. So it was take the derivative from like 3 to x to the 4th of tan. And maybe if you understood this conversation last class, then maybe you just know the answer right away. What is the answer to this?
4 times 4 third x.
Yeah. So the fundamental theorem of calculus says that the derivative of the integral of a function is just that function. So this is going to be like tan of x to the 4th. But then, back inside, for the derivative of x to the 4th. So, I don't know, if that's really actually all there is to it, it's just the chain rule. It's the chain rule applied to the fact that this is a composite function. But if you don't like this, some people don't, then we can kind of slow it down a little bit. And I can show you maybe an alternate way to think about this. And a way to think about this is by sort of making a variable substitution. So let's say, all right, let u be, define a new function, which is the integral from 3 to x of tan t dt. Okay? Then, by the fundamental theorem of calculus, what is u prime of x? It's just tan x. So, if somebody asks for the derivative of the integral from 3 to x to the 4th of tan t dt, really, they're basically asking you to differentiate what? Yeah, this is just u of x to the 4th. I want to take a moment and just like agree with that. Yeah. Okay. And what is the derivative of u of x to the 4th? Well, clearly now the chain rule is like required, right? And the chain rule says that this is just sort of like u prime x to the 4th back inside 4x cubed. And what is u prime of x to the 4th 4x cubed? Well, just plug x to the 4th into u prime. Tan of x to the 4th times 4x cubed. Alright, so thoughts? Cool. Alright, then I could just be a jerk and give you like a super weird hard one. Like this. What is the derivative of the integral from like sine x to ln x of root 1 plus t squared dt? How would I deal with this creature? If you start to think about this a lot, it gets even weirder. What is this actually doing? This is like a double accumulator function, right? This is like you have a lightsaber in each hand now or something, right? You're adding area on the left and the right. And at weird different rates that don't depend on x. So, I don't know, does anyone have any thoughts about how to actually do this problem? Yeah, Brian Morris says just split it up. In fact, that's just exactly what you do. You just split it up, rewrite this as the derivative of the integral from sine x to a of root 1 plus t squared dt plus the integral from a to ln x.
And then just like one's a backwards accumulator one.
One's a backwards.
One's a regular one.
Yeah, in fact, can I just be lazy and like flip this
Negative,
right now?
negative, flip it.
Yeah, so this is like negative a to sine x.
How do you know that you want to flip it out?
Because I just like fundamental theorem of calculus works only if it's like up here.
How it works.
All right, and then just apply this theorem, right? Or apply this strategy. So what would this be? Negative root 1 plus sine squared x times cosine x plus, in other words, making sense, roughly? 1 plus ln x squared times 1 over x. That's it. Alright. Don't worry about that too much. There'll be some home props on it. You'll either get it or not. Alright, now comes something that is really important. So integrals, so all the integrals that you had to do last night, okay, obviously they were all easy because of the fundamental theorem of calculus, but you may have noticed that they were back to giving you like really easy integrals, right? Yeah. What happens now if they give you hard integrals? What I want to talk about right now is substitution. So what I want to talk about is integration by substitution. Integration by substitution. Okay, how does this work? Well, suppose they give me some integral. I picked a nice example here that kind of explains things well, I think. Take the integral from pi over 4 to pi over 2 of 2 cosine 2x dx. Basically have two options for how to do this. I bet 90% of you, no, 100% of you would do the following. Well, you'd be like, dude, Mr. Rose, I know the fundamental theorem of calculus. The fundamental theorem of calculus says I just need an antiderivative. So this is, let's call this option 1. This is the lame option, by the way, that I'm going to try to discourage you from doing, but some of you will be stubborn and you'll just keep doing it this way forever, but you shouldn't. It works fine, kind of. It works fine, but it works fine. Option 1 is, first let's figure out what this antiderivative is. So option 1 says, all right, let's first settle the issue of what is the antiderivative of 2 cosine 2x dx. And then after having settled that issue, then I will apply the fundamental theorem of calculus. Seems reasonable. Okay, so how do you do this? I won't skip any steps. I'll do it all out. You let u be 2x, and then du is 2 dx, and it's looking perfect. So I therefore rewrite this problem as just cosine u du, right? And now I antidifferentiate. And therefore I get that the antiderivative of 2 cosine 2x is just sine 2x, right? Right?
Yeah.
Plus c. Okay. Having settled that problem to my satisfaction, I now return to the original integral, and I just apply the fundamental theorem of calculus to that integral, and I get that this is, well, it's going to be sine 2x evaluated at pi over 2 and pi over 4. Everyone do that right now? I got -1. Cool? Okay. Option 2 is this is the method which I recommend, which I prefer, and which you kind of need in certain isolated situations. And so I'm going to try to push you guys to do this, although it is kind of a new thing. And the new thing is we're going to do substitution, but we're going to do the substitution on the integral itself instead of sort of first solving the differentiation problem and then applying the fundamental theorem of calculus. We just perform the u substitution on the integral. And okay, what do I mean by that? So I'm going to go through the same process of making a substitution. So I'm still going to let u be 2x. But now, instead of just writing u equals 2x and not really thinking about it so much, I'm going to think of u as a function of x. So this is just really just the same thing, but I think it helps understanding. To think of yourself as defining a new function. And this function takes x values and outputs kind of like u values or something. And what is the derivative of this function with respect to x? Well, it's just 2. And we could write that as, du dx is 2. And so far it's really just the same thing. Du is 2 dx. Alright, and then that 2 is already sitting there. So I'm just going to perform the substitution directly on this integral. And 2 cosine 2x dx becomes cosine u, right? Cosine u du. Okay, but, and here is the important part, these numbers are x values. But I am converting this entire integral from a integral that involves x values to an integral that involves u values. So when I change the variable which I'm integrating with respect to, I need to change the upper and lower limits of integration also. These guys are x values. So I want you to sort of think of these numbers as kind of belonging to this variable. But when the variable changes, so do these numbers have to change. And what we get is this number actually needs to be converted from an x number into a u number. And how do we convert from an x number into a u number? Using the formula for converting an x number into a u number. So we just take u of pi over 2. And here we take u of pi over 4. Okay, and what is u of pi over 4? It's pi over 2, and because u is just a function which multiplies 2, and u of pi over 2 is pi. And so now I have simplified the integral into a different integral. And